We're going to actually show two different ways.
Which ones are dangerous?
And so the first one is a common demonstration. The idea is a supernova is an explosion that happens in a very massive star toward the end of its life. And the structure of that star before it explodes is pretty interesting. It started out fusing hydrogen into helium, and then it collapsed a little when it started to run out of hydrogen in the core and got hot enough to fuse helium, and then it's making heavier and heavier elements, and it ends up almost like an onion where the lighter elements are shells on the outside and heavier and heavier and heavier on the inside, things like oxygen and silicon, and right in the middle is iron. That is the heaviest element that will fuse normally in a star. But when you try and fuse iron, you don't get energy out of it like the other lighter elements. It takes energy, and so it just starts collecting in the middle of the star like a big ball of ash. And it gets more and more and more iron, and at a very specific mass, the gravitational pull is so strong that the protons and electrons get pulled into each other and form neutrons.
Wow.
It's similar to a reaction that happens in some atoms called reverse beta decay. We know beta decay is a neutron changing into an electron and a proton. Reverse beta decay is an electron being captured by a proton in the nucleus, and you end up with a neutron. So this huge ball of iron about the size of a planet collapses into a ball of neutrons because they're neutral. They can get a lot closer, about the size of a small city.
Wow.
So essentially, in the middle of this massive star, you have a void. And so those shells start falling from all directions. Remember, the heavier stuff on the bottom, lighter stuff on the top, and they fall in and bounce out. And that energizes the supernova explosion.
That's explosion that we see. Wow.
There's also some neutrinos created in that also are a big part of the pressure that blows the star up. But it's essentially like this common demonstration. We have the heavier elements. Maybe this is silicon, and then maybe this is a helium or something, and the center of the supernova, the star, has just collapsed. And so this is falling like this. And also keep in mind, it's three-dimensional, so that's one problem with this demo. I'm just going to drop these two. And maybe we'll try it on the table here.
Sure, yeah. Not
Usually
to do
we
that
do it on the floor. We'll do both if we're able to find it. And so usually I ask my students when I do this, can a ball bounce higher than where you dropped it from? So if I drop it from here, can the racquetball end up higher than that? And it can. Now it's a little more impressive when you do it on the floor, since so you got the idea. Now we'll see if I can, it's a little trickier too. And so
up and out of the studio.
So that's one supernova explosion. And you can get the idea. What's happening is this guy comes and hits and actually starts to reverse direction. And so it's really, you're seeing a collision like this. Even though they fell together, this guy hits first, starts to change direction. So it's a collision like this. So it's not surprising this guy goes flying off and takes some of the energy from the ball. But wouldn't it be great if students could actually measure that? And so I was playing around with some smart carts and got that to happen. So I have the red smart cart with two masses on it. So this would be the heavier atom. And the blue smart cart, no masses on it, it's a lighter atom. And there are, forces in between them. Those are being modeled by these springs. And I have our heavy spring. These, you can buy these separately as an accessory for the smart cart. I have the heavy spring in front of the red cart and the wimpy spring in front of the blue cart. And if I drop them from, about here, I'll hold my finger here, see if the blue cart bounces higher. And it did, and it didn't even hit the end stop, which
pretty nice,
was my plan. Now, because these are smart carts, your students can measure the velocity of each cart and even do a calculation for the kinetic energy. So that's what I have showing on the screen here. the top is going to be the velocity of both carts, the blue and the red. And then at the bottom, I have the kinetic energy of each cart. I just called it energy, but it is the kinetic energy. And so we'll hit start. And so you can see I guess it changed my color scheme, but that's all right. But you can see in the velocity graph that the velocity after the collision of the blue cart is greater than it was when it came in. So here they are going down the ramp. They hit and come to a momentary stop. But the blue cart's going faster, over 1 meter per second, when it hit going about 0.8. Now, where did that come from? Sure looks like it got it from the red cart.
Sure,
if we
yeah,
go down here to
decrease.
the energy, you can see the, I did put these in before. Oh, well. So the red cart's energy is the blue line.
we got them switched around, yes.
You can see it drops to very little here. And then the blue cart's energy is the red line, so it jumps up, it steals it from, that's just bugging the heck out of me. So in Capstone, you can change everything. And I had changed it before, and it didn't take, I guess. There we go.
Now
Isn't that better?
Yeah, absolutely.
Let's do it again,
right.
but let them bounce back and forth, and it's kind of fun to watch that, too.
Okay.
I've gone to... Well, you're, pretty brave standing close to the supernova, JP.
Yeah, well, I've learned being around you, Dan. You've never risked your life before.
And then some fun stuff happens. But so students can analyze this, and you can fit in some astrophysics into your physics classroom, which a lot of kids really get excited about. I mean, what could be more exciting than a supernova?
Nothing is more exciting than a supernova in the classroom. And you're talking about like the energy and the particles being thrown off, and we're looking at I'm assuming we're looking at the neutrinos being thrown off here? Is that
so the energy that powers the explosion comes from two parts: the kinetic energy of the atoms falling in, and the heavy ones give up a lot of that to the lighter ones and send them flying off. Also, there are nuclear reactions occurring in that collision, and those produce neutrinos, which normally don't interact with matter at all, but there are so many of them that astrophysicists calculate that's a significant part of the pressure that's blowing up the stars.
Right, and I think that's what we try to capture when we're measuring and looking for supernovas,
right?
We're looking for those neutrinos and that big flux of energy.
And those pieces flying out run into each other, and that can make heavier elements than iron. So a star only makes elements as heavy up to iron, but in that explosion, other heavier elements are made. Things like, well, I actually brought a piece of a supernova with me, although this might be a type 1 supernova. There's a piece of a supernova, gold.
Gold.
And so we would have no gold if stars didn't explode.
Wow. Now, there's an interesting fact for you. No gold if stars didn't explode. And that, ladies and gentlemen, comes from Mr. Dan Burns. Great demonstration. Really a wonderful demonstration.